Imagine being fully awake, fully intelligent, with jokes still loading in your head, but your body won't hit send. No wave, no text, no "I'm okay." Just a mind trapped behind a locked door. Now imagine this. You think, move the cursor left, and the cursor moves. You think, click, and it clicks. That isn't science fiction. That has already happened in clinical research using implanted brain-computer interfaces where people with paralysis controlled a computer cursor using intention alone. Today, we're talking about brain-computer interfaces, BCIs, implanted systems, non-invasive systems, and how they've already restored cursor control and even communication for some patients. Yes, we're going deep. But don't worry, I'll leave breadcrumbs. Brain-computer interfaces, when thoughts become clicks. At its core, a BCI is just a translation pipeline. First, read brain signals from outside the head or inside the brain. Second, decode patterns linked to intention, move, click, speak. Third, output commands to a device, cursor, keyboard, speech synthesizer. That's it. That's the entire magic trick, a translator between neurons and electronics. But the real question is, how do you actually listen to a brain? The first eavesdrop on the brain. History told as a story. Let's rewind to the early 1900s. Scientists are obsessed with electricity, and a German psychiatrist, Hans Berger, starts recording electrical signals from the human brain. This early work launches the field of electroencephalography, or EEG. Basically, Berger invented the world's first brain playlist. Unfortunately, most of it sounded like static and existential dread. EEG reads brain activity from the scalp. It's non-invasive, no surgery required. But the signal is faint, like trying to hear a whisper through a brick wall. Which brings us to the two big BCI families: non-invasive BCIs, EEG caps, external sensors, safer, easier, but noisier signals. Implanted BCIs, electrodes placed closer to neurons, clearer signals, higher bandwidth, but surgery and medical risk. So the trade-off is simple: safety and convenience versus signal quality and control. Now let's meet the people who made this real. Human core, the silent conversation. If you've never experienced paralysis, it's hard to explain what control really means. Because control isn't just movement, it's agency. It's the ability to still affect the world. In the BrainGate line of research, one of the most cited intracortical BCI programs, participants with tetraplegia have used signals from the motor cortex to move a cursor and perform point-and-click tasks. Researchers have shown repeatable cursor control even long after implantation in some cases. Imagine your arms are offline, but your brain quietly says, "Fine, I'll do it myself." And that's the emotional core of BCIs. Not superpowers, not telepathy, just a way back into conversation with the world. Trail marker number 2, cursor BCIs versus speech BCIs. BCIs tend to fall into different job roles. Role A, cursor control. Your intention maps to movement and clicks. Think a mind-controlled joystick. Role B, communication. If you can't speak or type, BCIs can help output language by decoding brain activity linked to speech or spelling. And this is where BCIs become both emotional and a little mind-bending. When thoughts become words. Deep rabbit hole, clear trail. Here's the thing. Your brain doesn't store speech like a book. It's more like a live jazz performance, timing, motor planning, patterns unfolding in real time. Yet researchers have demonstrated high-performance speech neuroprostheses using implanted recordings. One major study reported decoding unconstrained sentences from a large vocabulary at around 62 words per minute. Another reported large vocabulary decoding with large vocabulary for text in one participant, plus synthesized speech in research settings. 62 words per minute. That's not robot talk. That's I can argue with you in real-time speed. And that matters because communication is dignity. Non-invasive BCIs. Yes, they work, just differently. Implanted BCIs get headlines. They're dramatic. But non-invasive BCIs have been doing meaningful work for years. Take P300 spellers using EEG. These systems let some patients, including people with ALS in research studies, select letters based on their brain response to visual stimuli. Researchers have reported high-speed EEG speller approaches with strong information transfer rates in controlled environments. So yes, non-invasive BCIs can enable communication and control, but they often require strong attention, calibration and training, good signal conditions, and sometimes a saintly level of patience. Performance varies widely depending on the person and the setup. The in-between, less invasive implants. There's also a middle path, not scalp sensors, not open skull electrodes, but something in between. One example is an endovascular BCI approach, placing the interface through blood vessels rather than directly penetrating brain tissue. The COMMAND early feasibility study has evaluated such an implanted system for safety and feasibility. It's basically saying, I don't want to break into the house, I just want to install Wi-Fi from the plumbing. Reality check. This is medicine, not magic. Let's bring this back to Earth. BCIs are medical devices. That means serious engineering, serious ethics, serious regulation. The US FDA has issued guidance specifically addressing implanted BCI systems, including recommendations for testing and clinical considerations as these devices move toward broader use. The field is advancing. New feasibility studies appear. New investigational approvals emerge. That signals momentum, but it also tells us something important. Much of this is still clinical research, not consumer tech you can buy at the mall. Even companies in the BCI race are still navigating trials and approvals. For example, reports noted an FDA breakthrough device designation for an experimental vision-related implant, alongside ongoing work on implants aimed at helping people interface with computers. So the truth is, BCIs can restore some control and some communication for some patients, and that some matters, because one restored voice can change an entire family's life. Hope. Somewhere right now, a person is awake behind a locked door, and a tiny stream of signals in the motor cortex may be enough to crack it open. Not with miracles, with math, with medicine, with engineers losing sleep over noise and calibration, with clinicians and brave participants willing to try. And maybe, just maybe, the future isn't about turning humans into machines, but about using machines to return humans to each other. If you want part 2, comment Mind Mouse. And tell me, would you try a non-invasive BCI headset if it could type your thoughts slowly but safely? Like, subscribe, share, and I'll see you in the next story.